related to IBM supercomputer Deep Blue just beat the international chess champion Kasparov. So that's exciting news. You know, Kasparov is a legendary in international chess history. He got a champion when he was very young, and since he got the international chess champion, he was not beaten by any other human being in the following 20 years. But in 1997, he was beaten by a computer, Deep Blue. And after about 9 years, China developed a supercomputer called the Inspirteso. This supercomputer just beat Chinese chess champions, 4 champions in the same time. And after several years later, in 2011, again, IBM's supercomputer, Watson, just won the champion of Jeopardy. That's a kind of like a competition for humans' intelligence, challenging humans' intelligence. Now, this computer just won the human beings and got the champion in this game. So possibly we regard this computer as humans' intelligence, because like before, IBM Deep Blue or China's Inspirteso, those one human beings, we thought they just won because they have a powerful computing. One year after 2011, AlexNet just won ImageNet large-scale video recognition challenge. So AlexNet proposed by a team led by Professor Hinton and his students. Of course, we know Professor Hinton. We regard him the father of artificial intelligence or deep learning, and he won this year's Nobel Prize in physics. So they used deep learning and won the competition. And from that time, deep learning just exciting and encourage many other researchers to research in this regard. And after that researchers proposed several other very useful neural network. Now,
Sir, sorry to interrupt. Sir,
yes.
Actually, this thing will be deactivated after 10 minutes. So after 10 minutes, please join.
Oh, after 10 minutes, we change it to other one?
Yes, sir. Yes, sir.
Okay. Thank you. So in 2016, Google's AlphaGo won the gold champion, the CEDO. And 1 year after that, AlphaGo just beat gold champion Corti. Those are very exciting events, but after 6 years, so basically 2 years ago, OpenAI just announced ChatGPT. Now this just truly exciting everyone. I think right now many people use this to help them to find answers they are searching and help them to finish some work. And this year, I just want to mention, because my major is mathematics, so the other similar to ChatGPT, but focus on mathematics reference, that's harmonic. So hopefully in the future, harmonic will have a great impact like ChatGPT in language and this one in mathematics. And just 1 month ago, Meta scientists just are using deep learning method and they solve the kind of like more than 1 years old open mathematics challenge problems. So basically, to find the near proof function for the stable system. So that's unbelievable achievement for the deep learning or artificial intelligence in mathematics. And this year, we know the Nobel Prize in physics goes to Hopfield and Professor Hunter. And in chemistry goes to David Baker, Demis Hassabis, and Jumper. Now you know their work, that's the work they received as a Nobel Prize basically due to their contribution and the influence in artificial intelligence. And this is exciting. Now, artificial intelligence, as I said in the beginning, even though there is no uniform definition, but in my understanding for AI, artificial intelligence, definitely by the word, it's not natural. The intelligence is not human beings' intelligence. The intelligence is made by a human being. And the machine basically simulates some intelligence of people. How the machine gain intelligence? Basically, the machine obtains the intelligence through learning from the data. And we know data, of course, it's essential. Without data, machine cannot learn. Of course, the intelligence still need algorithm to implement the ideas, how to they learn. And during the process of learning, they need powerful computing. Now, in the following, I just want to introduce several algorithms. So basically one component of the artificial intelligence. Okay, so in the following, maybe I just use the other link. Hi, sir. Hi, madam. I just use the other link, okay? Since this will be over.
Hello, sir.
Yes, I just use the other link now.
Sir, okay, sir. Okay, sir. Please join. नहीं नहीं तो आप
And for buyers, basically, they can save money in buying the same amount of energy. So that's good for all of the sites participating in the microgrids trading. Now, since most of the microgrids, when they do the trading among themselves, they don't want to the other side know their information. So to predict the privacy of the participants, so we design a central unit, okay, or we call the central unit market operator. So all of the sites just pass their information to central unit. The central unit kind of just do the statistics, then relay the information to the other sites. But the exact information, the other sites don't know. So we form this model as multi-leaders and multi-founders stakeholder board game. Each player's action is private to his components and trading partners. And we regard signers as leaders. So the signers just find what's the best strategy for them. Now for signers, their strategies means their percentage of available energy, basically the percentage of the surplus energy to sell. Okay, that's their strategy. Suppose they want to sell their available energy in 10% or 50% or 70%. Okay. Then the seller sends their information available energy to the market operator or central unit. Now the central unit just collect all of the seller's information, then pass the information to the buyers. Then the buyers, when they receive the information, they just perform rolling automation based algorithm, choose the best action and send it to market operator. Then the market operator just they did before for the signers. They just collect the information and do the statistics and pass the information to signers. By the way, for buyers, their strategy, each strategy means the price they want to buy from signers. Okay. So for buyers, the strategy means the price they want to pay. But for signers, as I mentioned, the strategy means the percentage-wise of the available energy. Then the market operator pass the information to signers. Then the signers just run their algorithm and find the best strategy then send the information to market operator. So this process is just continuing until all of the sides think they already find their basic strategy. If they continue to do this, no change. So in this case, they just stop the algorithm and the game stopped. Now we can form this process as an optimization problem. So for seller and buyers, we use two utility functions to describe their benefits or the happiness. Basically, they pursue the most happiness. Okay, so basically the value is higher, they are happier. So they pursue the maximization of the utility function. Now for buyer, for example, the utility function is PS minus CJ, the difference times QJ. QJ, that's the energy for the buyer J got from the other sellers, okay? And the PS, that's the price for the buyer if they buy the energy from the main grid. Now CJ, that's the price for buyer to pay to get the energy. So of course we can say for this one, the price difference is bigger, they are happier. Okay? And of course, QG, if you get more, they are happier.
Sir, your mic is off.
Sir, your microphone is muted.
Oh,
Please turn on
okay.
it.
Okay. Now it's okay, right?
Yes, sir, it's fine now.
Okay. Yes. So I think all of the sides just pursue or find their basic strategy to make their utility function reach the maximum. Now, to design this, we use a very fundamental discover. If we can find a strategy to make the average of the utility function. Here, that's the definition. First one is the average utility function for sellers. A second one, that's the average utility function for buyers. If the algorithm finds the best action to maximize the average utility function, then it automatically solves the optimization problem. This is critical. Now, that's the algorithm we design based on the discover I just mentioned. Of course, there are still other details we need to take care to make sure our algorithm can get the results very quickly. Now, we just do the simulation in this IEEE 37 bus test feeder. In this power system, there are 5 microgrids, and microgrids 2 and 4 have a surplus of energy. So basically, they have energy to sell. And the other 3 microgrids, microgrids 1, 3, and 5, they are short of energy. They need to buy or buy the energy. Now that's the initial information for buyers and sellers. For buyers, for each buyer, they have 3 strategies or actions. So basically, each action, as I mentioned, for buyers, each action means the price they want to pay. So for the microgrid 1, it has 3 actions. They want to pay 22 cents, 28 cents, or 40 cents to buy energy. Okay. Now microgrid 3 has 3 actions too. Microgrid 5 has 3 actions too. Now for sellers, for the 2 microgrids, the available energy to sell or surplus energy, we already know. For example, microgrid 2, it has available energy 1,533. Okay. Now, for the 2 microgrids, each of them has 4 FALA action. So basically, finite action, not continuous, not means infinity. Now, when we do the trading, we can see now the 3 pictures showing the iteration, basically the results. What's the probability for the sellers to choose their strategy, basically the price? So for the first picture, that's a microgrid 1. And we can see for the red line, that's the first action. For the blue line, that's the second action. For the green line, that's the third action. We can see that they very quickly pick the one with the probability like 100. So they are kind of for sure after a certain time, they just pick the one action. Now the first one, we can say they just pick the first action. And they pick the one. And they can very quickly emerge into this action. So basically 22, right? Now for the other 2 pictures, represent the action they pick or the percentage-wise for the other 2 microgrids. And we can see very quickly they just pick all of this just pick action 1 with 100% probability later. Now, for this 2 picture in the left. Vertical side means the average action. So basically average cost. And the red line in the left, that's a equilibrium point. So basically that's the best action, best price. Now for this red line, we just get the best strategy by computing, and we don't assume the private information prediction. Basically, if we let each side know the other side information, then we can mathematically computing the best strategy, showing here, kind of like 23 cents. Okay, so from the picture here, we can see each microgrid, they just pick the one price closest to the best strategy, best price. Okay, now we can see this is very effective. So for the finite action, they always pick the one closest to the best action. In the right one, we can see the 3 microgrids, their average utility, basically the utility function, the value. They approaching to their maximum very quickly. Now this is for energy trading. Now in the following, we just look at the plug-in electric vehicle charging. We consider one factor, that's for overload, failure overload control. Okay, so when more and more PEV go into the market, now if we just imagine if all of the PEV charging in the same time, and definitely the peak time for the electricity usage maybe will go beyond the power grid's capacity. So in this case, it will maybe damaging the power grid. So we want to look at this problem. So basically here, we use PL represented the maximum loading capacity for feeder L. So PL equals XNT, basically the sum of XNT means the total load of P with DLT. Base code through the feeder L at T. Find L set of P with using feeding the feeder and to carry the power. So the last one, basically we consider all of the PV charging, the power usage doesn't go beyond the capacity of the feeder minus the basic usage. Now, we can form this as a minimization problem. So here, rho T depends on the usage of the electricity. This is an increasing function. Okay, so basically, when the whole power grid, the electricity usage is more, the electricity price is higher. So this one encourages people using the power when not many people using. So basically shifting the power to the valley. Of course, for this optimization problem, there are some charging rate constraint, like definitely bigger equal to 0 and not go beyond x and max. So the total energy requested to be charged should be equal to the demand, okay? Now the failure constraint is this one. Now this is a algorithm we designed to solve this problem. Here I don't go to the detail. Now this is a simulation. We did the simulation in attribute sorting bus. So in this one, we just set up the electricity price as a piecewise function. So the normal time, the valley time, and the peak time, 3 time period. Okay. Now, when we did this simulation, first picture, basically that's a node profile for 400 PVs and the base node without overload control and the fader L. So this one we don't do the faders overload control. Now, when we look at this picture, the blue area or the blue cover, basically that's a base node. Now the red area, red part, that's the PEV's usage. And the dot red line, that means that's the capacity of the fader. Now, if we don't do the fader control, we don't consider this factor in. So we can say in the evening, some time period, when we add the PEV's electricity charging and the base usage charging, we can say some parts go beyond the capacity of the fader. Now, the second picture, we do consider the fader's capacity. So when we do the control, we wish all of the time the PEV usage and the base usage, the total electricity demand don't go beyond the fader's capacity. And we did, you see. However, we may think with more condition, maybe the users need to pay more in the end. Now, this is a comparison of the cost for the customer when we consider the fader's overload control or without overload control. Red one, that's with the fader's overload control, this factor in, but it's the blue one without considering fader's overload. So we can say with time going, the normalized cost kind of same, no difference. Okay, now in the following one, I just want to quickly look at the economic dispatch optimization problem. So this one basically XD, that's a customer's demand. XI, that's ice generator generation. So basically, all of the generators surely generate the electricity just enough to satisfy the customer's demand. So basically, supply equal to demand, right? Now, each generator, definitely there are some constraints. So minimum, maximum generation. Now the optimization problem is to seek the total cost minimized. Okay. So to do this, we want to convert this to a consensus problem of multi-agent. So how do we convert it to the consensus of multi-agent? We look at the incremental cost for each generator. Incremental cost means suppose right now generate 100. Now if we increase it to 101, for the increase in one, suppose the cost increasing is 22, so the incremental cost for this generator is 22. Now we can see if the incremental cost different for each generator, then this is not reaching the optimization stage, right? Only when each generator, the incremental cost is same, then they are kind of reaching the optimization stage. So we convert this optimization problem to consensus of a multi-agent problem. Since my time is, I think, over, and the link maybe will be disabled soon. So I stop here. Thank you. Hello. Yeah, so I just stop here. I think according to my information, the link will be disabled in maybe 1 or 2 minutes. So I just stop here. If you have any question, you can ask me.
Thank you,
Before
sir.
the link is over.
Station and gain knowledge. I want to ask the audience, have you any question? Do you have any question?
Good morning, sir.
Good morning.
So I have one question.
Yes, go ahead.
Hello, good morning, Wang sir.
Morning.
Sir, can we apply any fuzzy MCDM approach on this technique?
Oh, that's good question. I think your idea is great. Why not?
Means
I think that's good. Yeah, you can use other method to solve the problem. That's
means,
my thought. Definitely, you can explore.
sir, means that
even
fuzzy Topsis method or fuzzy Vickers method, like that. Can we apply this kind of MCDM approach on this technique?
For I think it should be fine. Yes.
Okay, sir. Okay. Okay, sir.
Thank you.
Thank you, sir. Thank you.
Thanks.
Sir, I have
Yes.
one question. So,
Yes.
reinforcement learning, can we apply to any other field like this energy? This one you have just given the buyer and seller. So, can we apply to any other field? Can you suggest some fields, other fields?
Right now, I think reinforcement learning, this method applied to many computational fields. I don't think there is any problem you can apply to other fields, many of them. So yeah, you can just try. Thank you.
Okay, thank you, sir.
Thanks.
Thank you, sir. It was really a wonderful session. We are
Thank you.
really
Thank you.
thankful to you to be present here with us today.
Thank you so much.
Thank you, sir.
Have a nice
Thank you.
day. I have a successful conference. Thanks.
Thank you. Thank you.
Thank you.
Thank you, sir.
Thanks. Bye bye.
Bye, sir.
Bye, sir.
Bye.
So now we will take a short tree break and then we will be back here again after 10 to 15 minutes. Please enjoy your tea. Thank you, everyone.